consider important and general ideas and tips that are useful in BMO 1, BMO 2, and also other exams like AMC. The ideas are these 5, and also we have other ideas, but because there are so much general, I will tell you these things. For knowing the rest of the ideas, you can send message to my WhatsApp number in the description and comments. Okay. For example, first idea, small example, I can say in most years of BMO 1, 2, we see this idea. I will solve 2 problems with this idea, one from BMO 1 2021, one from BMO 1 2019. And after that, second idea, coloring and invariant. I solved 2 problems, BMO 2 2021, problem number 2, and BMO 1 2019. The next idea 3, is ideas in function. Consider, for example, small example, spatial cases. One is function 1-to-1, telescoping rule. We saw a problem of last year of BMO 2 2022 and BMO 1 2019. With this idea, the fourth idea is angle chasing cyclic quadrilaterals, finding them. We have 4 rules for cyclic quadrilaterals. And radical axes of 2 circles. I explained this in these 2 problems. Many problems of BMO that are in topics of geometry can be solved with these ideas, especially when it is not splash problem. Then we will solve BMO 1 2021 and BMO 1 2019. And last idea, fifth idea, in some problem you should consider different mods, and for example in BMO 1 2020, in BMO 1 2019, we will solve these 2 problems. And there are also some other ideas, we will work on them in next videos, and I said you can send message to my WhatsApp number. So let's start from first part, a small example, BMO 1 2021. This problem I've copied here, problem number 3. It says for each integer n between 0 and 11. Let me check. We have 2 problems. Sorry. It is problem of BMO 2 2022. And it is BMO 1 2019. Because BMO 1 2019 is easier, let's solve this first to understand how we work on a small example. Then we try BMO 2 2022 last year. So let's start here. It says a sequence of integers a1, a2, a3, and so on satisfies the relation 4an plus 1 squared minus 4an times an plus 1 plus an squared minus 1 equal to 0. For all positive integers n, what are possible values of a1? Okay, so that's the important thing in these assumptions. Okay, there are integers and we have this relationship. For all positive integers n, what are possible values of a1? At first, one important thing here, before working on a small example, is to find an plus 1, because here we have a term in terms of an plus 1 and an. We want to find an plus 1 is what in terms of, because we have only an, in terms of an is what? So let's work from the equation here. We have 4an plus 1 squared minus 4an an plus 1 plus an squared minus 1 equal to 0. So if we consider this part, you can see it is something squared. What minus what squared equal to this? It is 2an plus 1 minus an squared. We have this. And here we have minus 1. You take negative 1 to right hand side, it will be 1. So, because this squared is 1, we can conclude 2an plus 1 minus an equal to plus minus 1. So we have 2 cases. an plus 1. You take an to right hand side and divide by 2. It will be an plus minus 1 over 2. Now we have this. We found an plus 1 in terms of an. So let me write it here. We have an plus minus 1 all over 2. And then we want to work on the rest of the solution. So let's erase these things that we don't need anymore. Okay. In next step, what should we do? Now The problem says what are all possible values of A1, and we know there are positive integers or not, there are only integers. The sequence of integers, this for all positive integers. What are all possible values of A1? So, if we consider, for example, let's start, for example, A1 0. Then you conclude by this relationship A2 is A1 plus minus 1 over 2. Because it is 0, it will be plus minus 1 over 2. We will see it is bad, it is not integer. Why it happens? Because we have over 2, the numerator should be even. So, we conclude A1 has to be odd because plus minus 1 should be. So, A1 is odd. So, now let's check for A1 odd. We understand this by small examples, and easily we can say if A1 is even, then A2 is not integer. Now, let's consider odd numbers. Again, for example, from 1 we start. A2 is what? Is 1 plus minus 1 over 2. 1 plus 1, we can select one of them because both of them satisfy the main equation. 1 plus 1 over 2 is 1, 1 minus 1, so we know even number is bad for next term, like A1. If A1 is even, then A2 is bad. If A2 is even, A3 is bad. So we can conclude from here, because AN plus 1 is integer, AN should be odd. So we conclude 0 is bad. So A2 is 1. Similarly, we select A3 1 and so on. Let's consider A1, for example, negative 1, because they can be integers. A2 is negative 1 plus minus 1 over 2. It can be minus 2 over 2, minus 1, 0. Again, 0 is bad, it is odd. So A3 is negative 1, and so on. So here, if you check 3A1, 3A1, 5, you will see it works. And now I want to say always one of them even, like here, one of them odd, and we select the odd one. So let's check it. For example, suppose AN is odd, is 2k plus 1. I want to say AN plus 1 can get two cases, one of them is even, one of them is odd. Let's check. It will be 2k plus 1 plus minus 1 over 2. It will be 2k plus 1 plus 2 over 2, and 2k plus 1 minus 1 over 2, it will be 2k over 2. And it will be k plus 1 and k. So here, because they are consecutive numbers, one of them even, one of them odd. So always you have an odd case, you select that. Again, for next one, you select that. So we understand what are all possible values of a odd numbers, odd integers. The answer is that, and let me tell you, on your answer sheet, you don't need to write A1, for example, 1, 0, check this. First, tell that AN should be odd, prove this, because if AN is even, the numerator is odd, and AN plus 1 is not integer. And then say, okay, your claim is that for odd number works. Then you say if AN is odd, then AN plus 1 can get an odd number, and then the proof will be complete. Okay, let's solve a little harder problem. In problem number 3, BMO 20, BMO 2 2022, I want to tell you two things. One important idea that is useful in recursive sequence, and one important idea that is useful in, let me tell you, in induction, and also a small example. So let's work. Sorry, it was BMO 1. Let's correct this. 2021. Sorry, it was BMO 1 problem. I've made a mistake. It's not BMO 2 problem. So let's solve this. But it is a little harder than previous problem, than this problem. Okay, so let's read. It says for each integer 0 and from 0 to 11, Aliza has exactly 3 identical pieces of gold that weigh 2 to the n grams. So we have 2 to the 0, 2 to the 1, 2 squared, and 2 to the 10, and 2 to the 11. Okay. It says in how many ways, different ways, can she form a pile of gold weighing 2021 grams? That's this problem of 2021. It says 2021 grams. This year is 2022. It's good to consider prime factorization of 2022. For example, 2022 is multiple of 2 and 3. And if you divide by 6, it will be 3 times 6, 18. 22, 3 times 6, 18, 42. And 7. And 337 is prime number. Also, it's good to consider 2023 prime factorization. It's multiple of 7 or not. 56, 63. Yes, it's 7 times. 2 times 7, 62. 8 times 7, 63. 9, which is 289, is 17 squared. Okay. Memorize these years, prime factorization, the properties of these numbers. Now, let's start. I want to solve this with a small example. One important thing here. A small example on what? On N, on 2021. At home, when you want to try, you can check both of them, all of them, and then after solving some problem, you will understand quickly that what variable is good for working small examples on. Here, I will work on 2021. So, at first I say, if I want to create 1, we have only one way, 2 to 0. If you want to create 2, we can say 2 or 1 plus 1. 2 ways. So, let's call f of n is, or because we have n here, let's say f of n is answer for m instead of 2021. And the problem says f of 2021 is what we want to find that. So we can write 2 as 2 or 1 plus 1, which is 2 ways. 3, it will be 2 plus 1 or 1 plus 1 plus 1. 2 ways. Now for 4, we will say what? It is 4, 2 plus 2, 2 plus 1 plus 1, 3 ways. 5, you say 4 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1, 3 ways. For 6, you will say it will be 4 plus 2, 4 plus 1 plus 1, 2 plus 2 plus 2, 2 plus 2 plus 1 plus 1. It will be 4. So we will see 1, 2, 2, 3, 3, 4. We guess that the next one is 4. Let's check. 4 plus 3, you can say 4 plus 2 plus 1. Or we can say 2 plus 2 plus 2 plus 1. Or we can say 4, for 4, you can say 4 plus 1 plus 1 plus 1. And we can say also for 2, 2 plus 2 plus next to is 1 plus 1 plus 1. So we found 4 ways. So look, these things that we are working for a small example is for ourselves. You don't need to write them on your answer sheet, but you find the idea and then you say, for example, my claim is this. Okay, so for example, look, for 6, it is 4. For 5, it is this. So for n, we can say it is what? So let's write f of 1 is 1, f of 2 is 2, f of 3 is 2, f of 4 is 3, f of 5 is 3, f of 6 is 4, and we've calculated f of 7 is 4. So we guess that f of 2k, if it is even number, it is what? Look, because we have 2 2s, 2 3s, 2 4s, we understand that it is related to f of m to m over 2. So f of 2k, you say divide by 2. K here, it will be 1. If you divide by 2, you add 1. Then this one, okay. This one will be okay. This one, okay. And f of 2k plus 1 will be what? If we check, for example, here 1, we will see it is also k plus 1. Our claim is this, and we want to prove this. So here we should see how we can prove this. We can say it is like recursive sequence. And one important thing, that if you want to also solve IMO problem, and you want to solve a recursive sequence, you should see M represents what? M represents, for example, 2021 grams, M grams, it says. So then consider first or last for example, first grams you want to create. And also we have some weights. 1, 2, here. 1, 2, 4, 8 to 2 to the 11. So if I want to create 2k, I want to create 2k. 3 ones, 3 twos, 3 fours, 2, 3, 2 to the 11. Because we want to create 2k and 2k is even, and all these weights are even, I can only use even number of ones. So number of ones can be 0 or 2. If I want to use 0 ones, then what happens? I use some combination of 2's. We don't know how many. Then I will want to use some combination of 4 and some combination of 2 to the 11. And it should be 2k. So I divide by 2, then it will be some combination of 1's, some combination of 2's, and some combination of 2 to the 10. So we have equivalent thing because we've divided by 2. It starts from 1, so it will be. And like here, we can say in k, and we want to find 2021. In 2021, we don't need to use 2 to the 11. We can say it is equivalent to create k, and we know that all m we want to create is less than or equal to 2021 because the last term we want to find is for 2021. So k, 2k is less than or equal to 2021, and k here, so each case of k is equivalent to case of 2k, so you say here it is equal to f of k. And then if you have 2 ones, then again you can say we have exactly 2 ones, some combination of 2's, some combination of 4's, and so on to some combination of 2 to the 11. It will be 2k, and then I subtract these 2 ones, it will be some combination of 2's, some combination of 4's, and some combination of 2 to the 11. Maybe 0. Then it will be 2k minus 2. I subtract 2 ones from right hand side, also from both sides. Then I divide by 2. It will be some combination of 1's plus some combination of 2's plus some combination of 2 to the 10. And because we've divided by 2, it will be k minus 1. So this part will be f of k minus 1. So we've concluded that f of 2k equal to f of k plus f of k minus 1. Now, I want to use induction to prove this. So this claim we can use base case we've proved. For base case, we can say, for example, k equal to 1. Or this one, for example, f of 1, let me tell you. F of 1, f of 2, for example, we said they are correct. And also you can use f of 3, 4, any of them you want. It depends on the solution. So let's finish the solution first. Now, I want to use f of 2k, and I want to use induction. I consider for 1 to 2k minus 1, the claim is correct, and I want to prove for 2k. So f of 2k equal to this. You should consider cases. K is odd, k minus 1 even, or vice versa. But I can do something to not consider cases. I can say f of n is what? It's a good example, a good exercise. You know these things? Can you tell me f of m is what if we want to use these two things? If you pay attention, it will be m over 2 floor of that plus 1. And here, I can say f of k is what? K over 2 plus 1. F of k minus 1 is what? K minus 1 over 2 plus 1. And we know that because one of them is even, one of them is odd, one of them has negative 1 over 2. So you say k over 2 plus k minus 1 over 2 minus 1 over 2 plus 1 plus 1 plus 2. So k over 2 plus k over 2 is k minus 1 over 2 minus 1 over 2 is negative 1 plus 2 is 1. So I've proved for f of 2k. So now try to prove f of 2k plus 1 as homework, and you can comment your answers right below this video. It is exactly like f of 2k. And we've proved completely this problem. So let's go to next idea. Coloring and invariant. I will tell you 2 important ideas in coloring and invariant, and then we solve these 2 problems. We have three colorings. One of them is checkerboard scheme. %90 of coloring problems can be solved by this. You consider black, white, black, white, black, white. And then if you want to fill with dominoes or 1/2, the number of blacks should be equal to the number of whites if you want to tile. And also it can be useful in other problems we will solve. The problem of BMO, you will see how useful it is. One other way is general form of checkerboard scheme. In that way, for example, in checkerboard scheme, we have black and white. And black and white means what? Means we have two colors. And it is good when we have, for example, 1/2 tile or domino. But sometimes, for example, our tile is 3 or 4. Then checkerboard scheme is not so much useful. But here, we can do something. We can color with 3 colors. So let's see. You say 1, 2, 3, 1, 2, 3, 1, 2, 3. You go like this. And this one, 1, 2, 3, 1, 2, 3, 1, 2, 3. Here, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Look, it is increasing. Here, it is increasing. If you consider both of them decreasing, it will be same as increasing. What? If it is increasing, at first I checked only one of them, but in one problem I saw that okay, there are some problems that second type works. So if I color here with 3 colors, 1, 2, 3, here it is increasing, you say 1, 2, 3, but here decreasing means after 1 you say 3. Okay, then it will be what? It means the next cell is 1 before that, 3 before that, 2 before that, 1 before that, 3. Here it is increasing, it will be 1, 2, 3. Here it is 3, 1, 2. Here it is 2, 3, 1. And 1, 2, 3. And let's see the uh, arrangement is different. For example, the places of ones. So why it is useful? If you have this cell, for example, 2, 3, 1, or if you place like this, it will be 3. For example, in increasing, it will be 3, 1, 2. So if you want to tile a table with this, number of ones should be equal number of twos, should be equal number of threes. And we conclude that this necessary condition should be satisfied. We have also another condition you should pay attention on also on the other things. Maybe it's not possible to color, but it is necessary condition. Third one is columns coloring. And in this way, for example, if you want to tile with this, so you color 1, 1, 1 first column, second column 2, 2, 2, so on. 3, 3, 3, we color with 3 colors. 1, 1, 1 again. And if you select like this, we select from each color once, for example, 2, 3, 1. But if you select horizontal, we select, for example, from one color 3 times. So in this case, the number of cells with color 1 minus the number of cells with color 2 is multiple of 3. Also, number of 1 minus number of 3 cells with 3, number of 2 minus number of 3. Why? Because, for example, at first, if we select a horizontal, we add 1 from each. We select 1 from each of them. If we use horizontal, for example, from 2, we select this. Again, if we select horizontal from vertical from 2, we have this. If we select vertical from 1, we have this. If we select horizontal, we have this. As you can see, all the difference of each two colors, always the difference is multiple of 3. Now, first, let's solve this BMO 2 2021. It says Elisa has a large collection of A by A and B by B types, where A and B are positive integers. She arranged some of these tiles without overlaps to form a square of side length n. Prove that she can cover another square of side length n using only one of her two types of tiles. So it says at first we have n by n, and we tile this with a by a and b by b. And then it says at the end we can fill n by n by only a by a or b by b. So we should prove a divides n or b divides n. It means n is multiple of a or b is multiple of a. Now for this problem I use columns coloring, the third idea. With how many colors? Let's solve with a colors. 2 to a. And now let's use contradiction. So contradiction is a doesn't divide n, b doesn't divide n. So n is a cubed plus r, which r is not 0, r is at least 1, less than or equal a minus 1. So at the end, when you write, it will be this column r, this column 1. We have this. So if we consider n, number of cells from 1 minus number of cells from a equal to n cells. We have this. Now, when we select a by a, we select from all of them equal. But when we select b by b, if we want to have any difference, because the columns are b by b, so the difference can be created by something multiple of b. So b has to divide the difference. Like the idea here, I said the difference can be created by 3, it is multiple of 3. Here, if you have more from one color than the other color, because each column has b cells, so we select from each color b, again from other color b, so the difference should be multiple of b. So we used a doesn't divide n, and then we concluded this, and then we reached b divides n. So that's a contradiction, and we proved this problem. If you have question about the proof of this or other, you can send message my WhatsApp number in the description and comments. Now, we've solved this one. Let's solve 2019, BMO 1 2019. It says we have 6 children are evenly spaced around a circular table. Initially, one has a pile of n sweets in front of them and the other have nothing. So, okay, let's draw this circle. It says one has a pile of n sweets in front of them and the other have nothing, and there are 6 children. It will be this up to here. It says if a child has at least 4 sweets in front of them, they may perform the following moves: eat 1 sweet and give 1 sweet to each of their immediate neighbors and to the child directly opposite them. So, for example, if he wants to do something, it will go to, for example, n minus 4. It will be plus 1, and this one plus 1. An arrangement is called perfect if there is a sequence of moves which result in each child having the same number of sweets in front of them. So we want to reach the case that all of them equal to 2. It says for which values of n the initial arrangement is perfect. So at first try to use a small example as pause the video and try to solve. If you don't see live, you can pause the video and try to find small examples for what n is possible and try to find at least one example. If you can do that, then you can find the solution is in an easier way. Okay, so let's see. Here, if we have this. For example, here we have A, here we have B, C, D, E, F. If we use checkerboard scheme, means alternatively black and white. So for example, it is black, this one white, this one black, this one white, this one black, this one white. Then you subtract 4 from here, plus 1, plus 1, plus 1. Now, if I consider, for example, let's consider black will be -4 and white will be what? Plus 3. Or white will be -4. It depends on that we select which child. It will be plus 3. So we can say black minus white. In first case, it will be -7. The change, this first second case will be +7. So we can say, because at the end we want to reach what first? Let's consider this as f. In first case, f is n. In last case, f is 0. And it changed by n 7 by 7. So from this one, we conclude 7 divides n. We call this invariants and use coloring, that you find some property that is constant. For example, the remainder of f when divided by 7 is constant. It is one coloring. Now I want to consider another coloring. So let's consider here. It is A, it is B, it is C, it is D, it is E, it is F. If you use a small example, you will understand that probably it should be multiple of 4n. And now we want to see how we can prove it. If we consider this one, and for example, let's consider this. It will be -4 plus 1. It's not so much good. What if we consider these two things only? And it will be -4 plus 1. Let's consider, for example, this cell minus this cell. Let's consider. This is black, this is white. Here, let's consider black minus. Here I don't mean number of blacks, means the sum of the blacks. So here, black minus white, let's see what happens. If we select A, it will be -4. If we select B, it will be 0. It won't change. If we select C, it will be +4. If we select D, again it will be 0. If we select E, again it will be 0. If we select F, we add 1 to A, 1 to C, again it will be 0. So we understand here, and let's call this one G. It changed by 4. So in the first part, G is n, this minus this, and in the last case, G is 0, so it changed only by 4. So 4 divides n from this part, we conclude. And then from these two things, we conclude that 28 divides n. Now I want to prove that for 20 n, that is multiple of 28, it is possible. Okay. Now suppose n is 28k at first. For yourself, try to check 28. How we can reach to 0. 28, 0, 0, 0, 0, 0. If I select the 7 times, it will be 0. 6 times, let's check this 6 times. Select this. It will be 4, and this one will be. Let's use 28 7 times. So it will change to what? 0, 7. 7, 7, 0, 0. Then let's do it once, do it once, do it once. So then we conclude. This one will be -4, 3. This one will get from this. These ones from this. It will be 3, 3, 3, 3, 3. It is for ourselves. 28. Now I use this way for 28k. So 28k, 0, 0, 0, 0, 0. Then I use 28k, how many times? 7k times. So it will be 7k, 0, 7k, 0, 0, 7k. Then I use each of them k times. All of them will be -4k, so they will be 3k, 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 3k. Because k times k to this, k to this, k to this, so it will be 3k, 3k similarly 3k. It is possible. So we've proved for multiples of 28 it's okay. Otherwise it's not okay. Now, third idea is ideas in function. We have two problems. One from BMO 2 2022 last year and the other BMO 1 2019. And these two function problems we want to use same ideas. Let's solve first this problem of BMO 2 2022. The ideas are similar. And also the difficulty, we can say BMO 1 2019 is more difficult than BMO 2022. Okay, so let me tell you some ideas in function problems. Try to find f of 0 if possible, f of, for example, plus minus 1. And these things, special cases, if you have, for example, two variables, consider x equal to y, x equal to negative y. It means consider special cases. And when you have something, for example, like this part, it is a complicated term, f of inside f. This try to get rid of complicated terms. How? Complicated terms. How we can get rid of complicated terms? You can write, for example, two equations. For example, you can write it for y and w, and then subtract or something like this to get rid of this to reach a better thing. And check function is f1 to 1 or not. And many other things, telescoping rule. If you want to learn them, as I said before, feel free to send message to my WhatsApp number in the description comments. Okay, so let's start. It says f from the positive integers to positive integers. So here we can check, for example, f of 0, f of negative 1, because it is from positive integers to positive integer. And 2y f of, so let's write this, 2y f of x squared. Let's see. Plus x. Or equal to f of x plus 1. F of 2x. Okay, so here, if I want to get rid of this, I write it for yw. Okay, so 2y f of 2w, sorry. yw xx, 2w f of x squared plus x equal f of x plus 1 f of 2xw. And then here we can divide both sides. Divide first one over second one. And why we can do this? Because yw f of them are positive integers. They are not zero, so it's possible to divide. If you divide, left hand side will be y over w. Right hand side is f of 2xy over f of 2xw. So here, if we cross multiply, y f of 2xw equal to w f of 2xy. And then, if we consider y equal to 1, we reach f of 2xw equal to w f of 2x. We have this, and if we consider also x is 1, then we can conclude f of 2w equal to w f of 2. So let's consider f of 2 equal to c, okay? F of 2 is a constant. Or let's consider f of 2 is r. So it will be wr, f of 2w. So we found even numbers in terms of f of 2. Or okay, so it is the first thing we've reached. Now, let's see how we can use it in main equation. 2y f of x squared plus x equal to f of x plus 1 f of 2xy. Because we've reached this, f of 2xy is even. So it will be, if we use this WRC, so it will be, you should divide it by 2, it will be W times R. We should divide it by 2, xy times R. Xy R. So we cancel y, and we reach 2f of x squared plus x equal to f of x plus 1 times xr. Now, because we know f of 2w is what, I consider here x equal to 2k. So it will be 2f of 4k squared plus 2k equal to xr, which is 2kr, times f of 2k plus 1. And I know that f of 2w equal to wr from this part. So the first one, you should divide it by 2 times r. It will be 2k squared times r. Then for this part, you divide it by 2, k squared times r plus k times r. And then if you multiply by 2, it will be 2k squared r plus k times r equal to 2kr, f of 2k plus 1. So because we know f is from positive integer to positive integer, so 2k is positive and k is positive. So we can divide, we can divide both sides first by 2, then by r, then we divide both sides by k. Left side will be kr plus 1, and it will be f of 2k plus 1. So if I want to write f of 2w plus 1 equal to what? wr plus 1. So we found f of odd numbers and even numbers in terms of r. We've replaced in this equation x with 2k. Now I want to replace it with 2k plus 1. So x is 2k plus 1. And if you write, it will be 2f of 2k plus 1 squared plus 2k plus 1 equal to f of 2k plus 2, the whole term, times 2k plus 1r. Now this part, if you calculate, it will be 4k squared plus 4k plus 1. It will be like this. You should subtract 1 to w, divide by 2. W times r plus 1. So here, f of this, it will be 2k squared plus 2k times r. Then this part is even again, is odd inside the f. It will be, you divide by 2k squared plus kr plus k times r plus 1. And f of 2k plus 2 is k. If we apply this, it will be k plus 1 times r. So let's write this whole term 2 times. Let's see, can we cancel anything here? Sorry, here we should add 1 because it is, if you want to apply this, it will be divided by 2 plus 1. Okay, so here if we add 1 plus 1 will be 2. It is even number if we use. So then we use this. It will be what? You divide by 2 times r, and it will be k squared plus k times r here plus k plus 1 times r again. And then we cancel this r with this r. And f of 2k plus 2, we said is, it is even number, it will be k plus 1 times r. So the left side is k squared 2 times. And here I can write it k times k plus 1, so I can factor from k plus 1. It will be 2k plus 1, kr plus 1. and right side will be k plus 1 times r times 2k plus 1. Now, because we know k is positive, because 2k plus 1, and k plus 1 is obviously positive here, because k can be from 0, and we cancel these two things, we divide, it will be 2kr plus 1, so let's write 2 times kr plus 1 equal to r times 2k plus 1. Now we know it is correct for infinitely many k's, because it all numbers. So, I can write it as a polynomial is k 2r minus 2r, they will be cancelled, let's check, yes, plus 2 minus r equal to 0. So this part is 0, so we conclude 2 minus r is 0, so r equal to 2. Because r equal to 2, we conclude it is 2w, and this part is 2w plus 1. So it means what? F of x is x. Because for both even and odd, we have this. Now, at the end, you should check in the main equation that does it satisfy or not, identity function. It should be x squared plus x, f of that, let me write, f of that will be x squared plus x, right hand side is x plus 1 times 2xy. If we check left hand side, if we factor x from this part, it will be 2xy times x plus 1, and we will see it satisfies. So the answer of this problem is f of x equal to x for all x that are positive integers, because this function is from positive integers to positive integers. Now, let's work on second function problem. It says a function f is called good if it assigns an integer value f of mn to every ordered pair of integers mn in such a way that for every pair of integers mn we have 2f of mn equal this. So, as I said in the ideas for functions, I said consider, for example, f of 0, special things, a small examples. So, at first focus on finding f of 0, 0. If you replace m with n with 0, and let me write, it is first equation, it is second equation, or let me tell you something better. It is first term, second term, third term. Because first term equal to second term, m equal n equal 0 to f of 0, 0 equal to f of 0, 0 plus 0 plus 0, which is 0. So we conclude f of 0, 0 equal to 0. The first term that we've reached. Here, we've replaced m equals 0, n equals 0, and we found f of 0, 0 equal to 0. Now, in next step, I, for example, want to find, here you will see that we have m minus n, n minus n. So if we increase m and n by a constant, for example, by 4, here they will be cancelled. So let me tell you, we can say 2f of m plus k, n plus k. We want to use 1 equal to 2. So replace m with m plus k, n with m plus k. But in next term, m minus n, n minus m. A k will be cancelled, plus m plus k plus n plus k. So we can conclude what? We have this term, which will be f of m minus n, n minus m, plus n plus n plus 2k. Now, if I write it for mn, 2f of mn equal to f of m minus n, n minus m plus n plus n. So we conclude 2f of m plus k, n plus k equal to 2f of mn plus 2k. And if you divide by 2, both sides by 2, f of m plus k equal to f of mn plus k. And it is the second thing that is good. Let's consider it is fourth. And it is, let's show a rectangle around this. And this part is 5. Okay. Now, we want to start finding f of 1, 0, f of 2, 0. So, In next step, let's write the equation 2f of mn equal to f of m minus n minus m plus m plus n equal to f of m plus 1n plus f mn minus mn plus 1 minus 1. Okay, we want to find f of 1, 0. First, let's replace m, for example, with 1 and with 0, and it was 1, it was 2, it was 3, and let's use 1 equal to 3. Then we can calculate 2f of 1, 0 equal to f of 2, 0 plus f of 1, 1 minus 1. F of 1, 1 is what? By applying this, we can say, for example, f of kk, if m equals 0, we know f of 0, 0, it will be k. So, I can say f of 1, 1 equal to, okay, f of 1 is 1 because f of kk is 1, and we can find f of 2, 0 in terms of this. So, let's consider f of 1, 0, c a constant. We want to find them in terms of c. So, 1 negative 1 will be cancelled, and we conclude f of 2, 0 is 2c. So, as homework, try to prove that f of k0, similarly, you should divide it to 2 parts one way, is kc. Divide it to 2 parts, k is integer. Divide to 2 parts, k positive, k negative, and with induction, you can prove it. If you have problem how to prove this, feel free to send message to my WhatsApp number in the description and comments. Okay. So f of k0 is kc. Now by this thing, and let's call this one the numbers here we had. Let's call this one, for example, 6. And here we've used 6 for this part. Least part 7, that's all of them. So if we combine 5 and 7, f of mn equal to, we can say f of m minus n0 like this part. If we want to reach from this to this, it was plus n. So k here is n. Plus, here it says plus n. F of m minus n0 by 7, this part you apply 7, this part you apply 5. By 7, it will be n minus n times c plus n. Okay. So we found that f of mn is what? M minus n times c plus 1. So let's check our main equation. First term is 2f of mn. So it will be, we can write it as mc minus nc plus n. So it will be 2 times mc minus nc plus n. Which will be what? We should multiply by 2. It will be 2mc minus 2nc plus 2n. Let's use 2 f of m minus n. So let's call this one 8. So 2f of m, we are using 8 for each part, for this part. F of n minus m plus n plus n. If I apply 8 here, it will be first one c minus second one c. So it will be m minus n c minus n minus mc plus n minus m second one plus m plus n. So m and negative m will be cancelled. Negative nc plus mc plus mc. Okay, so it will be 2mc minus 2nc plus 2n. So we will see these two things are equal. If we use third one, let's write third one here. F of m plus 1 n plus f of m n plus 1 minus 1. So f of n plus 1, if we apply 8 here, it will be n plus 1c minus nc plus n plus mc minus n plus 1c plus n plus 1 minus 1. Minus 1, this will be cancelled. C here we have, let's see, negative c. Here we have, so let's see, negative c here. C here. If negative c will be cancelled, mc, it will be 2mc minus nc minus nc minus 2nc, and then this part plus n. Also here we have n plus 2n, so we will see all these three terms are equal. So but c should be integer because the problem says f is from integers to integers. Now we've solved this problem, and do this one as homework, induction, and you can write your solution below this video. Let's work on next problem, angle chasing cyclic quadrilaterals radical axis. We want to solve these two problems with these ideas. BMO 1 2021 and for last year, BMO 1 2019. So let's solve first BMO 1 2019. It's a little easier. And then when you are ready, we solve next problem, which is BMO 1 2021. Okay, let me show the figure. It says two circles S1, S2 are tangent at P. Then a common tangent not through P touches S1 at A, S2 at B, for example, something like this. Points C and D on S1, S2 respectively are outside the triangle APB. We have triangle APB. With what property? Such that P is on line CD. Okay, so let's draw them with different color. It will be something like this. CD. Then it says prove that ACBD are perpendicular. So if I draw them, BD will be this, AC will be this. Then we call, for example, this one N. We want to prove that N is 90. Now, here when you see two circles, they intersect, we call this line radical axis. If they are like this, common tangent is radical axis. If they are like this, internally tangent, common tangent is radical axis. So if I want to draw radical axis here, then I can say it is alpha, it is half of this arctangent chord angle. It is also alpha, it is also alpha. This is beta, it is beta. So here in triangle APB, sum of angle equal to alpha 2 beta equal to 180. So we conclude alpha plus beta equal to 90. Then if you consider triangle CDN, alpha plus beta is 90, so n equal to 180 minus alpha plus beta. Alpha plus beta we bridged here is 90, so it will be 90. We use it here. So we prove this problem only working with angles. You know, angle chord, angle, inscribed angle, central angle, interior angle, exterior angle. If you want to know all these angles, cyclic quadrilaterals are important. We have 4 rules. If you want to know them, as I said before, feel free to send message to my WhatsApp number in the description and comment. So let's solve last year BMO 1. It says two circles. Let me draw. Okay, two circles gamma 1, gamma 2 have centers O1, O2. Respectively, they pass through each other's centers and intersect at A and B. The point C lies on the minor arc of BO2 on gamma 1, yes, BO2, gamma 1. The points D and E lie on the line O2C such that AO1D, let me show you here, AO1D equal to DO1C. So it means what? O1D is angle bisector here. So we can call, for example, this angle alpha, this angle alpha. And then CO1E equal to EO1B here. It means that O1E is angle bisector of CO1B. So if you want to find E and D, you can draw like this. So we call this part beta, this part beta. Prove that triangle D1OE is equilateral. D1, DO1E. Okay, DO1E. Now, this says a minor arc of a circle is the shorter of the two arcs with given endpoints. Okay, so let's, now that we know the problem is what, okay, here DO1E. Now, I want to prove it is 60 degree. How? Look, O1, O2, I want to prove R1 equal R2. O1, O2, we can say it is equal to R1 equal to R2 also, so they are equal. And it is equal to O1A equal to O2A, so O1, O2A is an equilateral triangle, so it is 60. This angle is also 60. This angle is 60. Now, here the first thing I want to prove why this angle is 60. We can say, let's consider this angle by similar way. Okay, so look, let me write for you that 60 degrees. We said this angle is 60 degrees because AO1, O2 is an equilateral triangle. Also, BO1, O2 is an equilateral triangle, so it is also 60. So we can say AO1B equal to 60 plus 60, which is 120. And also it is equal to 2 alpha plus 2 beta. So we conclude alpha plus beta equal to 60 degree. So this angle is alpha plus beta. So the first angle we proved DO1E equal to 60 degree. It was the first one. Now I want to prove one more 60 degree to prove that DO1E is an equilateral triangle. I say if I prove this is 60, the problem will be solved. But because it is 60, I said we have 4 rules for proving cyclic quadrilateral. One of them is equal angles see the same side. So we can say O1D O2 equal to 60 is equivalent to prove that AD O2 O1 is cyclic. Now for proving this, I say, let me erase this part. I try to prove this angle by this angle equal alpha because this angle equal alpha. So I should prove why it is alpha. Now we can say if I want to prove it is alpha, I should prove this part why it is 180 minus alpha. Now, this part, see what arc, see this arc. Let me write with other color. It's inscribed angle and see this arc. Okay, so, and we can say because it is 2 alpha and it is central angle. So this part is 2 alpha. So this arc is 180 minus 2 alpha. 360. The whole circle is 360 minus 2 alpha. And half of this will be 180 minus alpha. So it is 180 minus alpha. It is alpha. So this part, we wanted to prove that it is cyclic. We proved this and the problem has been solved. So look, these types of problem working with angles, angle tracing, cyclic quadrilaterals, this thing is useful in many problems of BMO 1, especially when the problem is from 1 to 4. Okay, if you want to learn other geometric formulas, ideas, as I said before, feel free to send message to my WhatsApp number in the description and comments. Fifth idea, considering different modes. In these types of problem, It is the last idea in this video, but not the last idea in all, because I tried as much as I can to tell the important ideas, and if you want to know rest, you can send message to my WhatsApp number in the description and comments. Let's solve these two problems to understand considering different mod is what. The first problem, BMO 1 2020, the next one BMO 1 2019. Okay, let's solve this problem. It says in the equation a to the AA plus AA equal to BBB, CDED, BEE, BBB, BBE. The letters A, B, C, D, and E represent different base 10 digits. So the right hand side is 16-digit numbers and AA is a 2-digit number. Given that C is 9, find A, B, D, and E. So C is 9. Now, at first I tried to find AA. A is what? So, left hand side. Let's focus on that. If A is 1, obviously it is not possible because 1 to the 11 plus 11 is 12 and it's so much small. We want 16-digit number on right hand side. So, if A is 2, it will be 2 to the 22 plus 22. We know it will be 2 to the 11 squared plus 22. 2 to the 11 is 2048 plus 2 squared plus 22, which is less than 3000 squared plus 22, which will be 3 times 9 times 10 to the 6 plus 32, which is not 16 digits. So A2 is bad. Now, for A4 also, I want to tell that it will be so much larger, then we understand A3 is good. 4 to the 44 plus 44, it will be 2 to the 2 squared, 88 plus 44. It will be 2 to the 10 to the 8 times 2 to the 8 plus 44. 2 to the 10 is greater than 1000. It will be 1000 to the 8 times 2 to the 8 is 256. Plus 44, 1000 to the power of 4, it will be 1 to the power of 24, so it has more than 16 digits. So from these things, we conclude A is 3. It's the first important thing. So A is 3, we can replace it. So the first thing we found, A is 3. 3 to the 33 plus 33 equal the rest. BBC, DED. The next 3 is BE. The next 3 is BBB, BBE. BB. Okay. Now, let's consider, for example, I want to find E. Because it is last digit, I consider mod 10. 3 to the 33. Look, I am considering different mods from here. First mod 10. So if I consider mod 10, it is what? It is 3 squared to the power of 16, which is 32, times 3 plus 33. So it will be 9 to the power of 16 times 3 plus 33. Because it is mod 10, 9 is negative 1. Negative 1 to the power of 16 times 3 plus 33, I can write instead of 33, 3. So here it will be 3 plus 3 equal to 6. So we conclude also right hand side mod 10 is E. So E is 6. Now I can write this E is 6, this E is 6, this E is 6. Okay, now another important thing is to consider mod 9, sum of the digits. Left hand side 3 to the 33 is 0, 33 mod 9 is 6. Is congruent to 1b, 2b, 3b, 4, 5, 6, 7, 8, 9. It will be, let's count again, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9b, which will be 0, it's good. For C, 1c, we have only 1c, and we know C is what? From assumption of the problem, C is 9. Plus How many D's are there? 1, 2, 2 D's. How many E's are there? 1, 2, 3, 4. 4 E. So we've considered E, we've considered B, we've considered C and B. Okay, if we consider mod 9, 9B and C will be cancelled. 2D plus 4E. 4E, it will be 4 times 6, 24. So if we consider mod 9, 24 mod 9 is 6. So 6, 6 will be cancelled and D mod 9 will be 0. But, so we conclude D is 9 or D is 0. But because the problem says there are distinct digits, let me find it, represent different base 10 digits. So because we know we had one digit that was 9, what digit? C was 9. D is not equal to C, so D is 0. So we found, so far D is 0. We found that E is 6. We found A is 3. So what is left? B. Mod 11 is good for B. And the reason why B is mod 9, we should consider some of the digits. It is because 10 mod 9 is 1. For 11, you should start plus, minus. The reason is 11 mod 10 is negative 1. If you want to know with details the proof, as I said before, you can feel free to send message to my WhatsApp number in the description and comments. So let's consider plus, minus, 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 plus, minus. So here, 2, 3, 4, 5. Okay. Let's consider mod 11. Left hand side is at first. Let's focus on 3 cube. Let's first consider right hand side. The coefficient of E, we have 1 plus E, 2 plus E, 1 plus 1, 2. 2 plus 2 minus 1, 0. They will be cancelled. And plus E again, so it will be 2E. Now let's consider D. Minus D, minus D, minus 2D. Then consider C. It will be plus C. Let's consider B. This B will be cancelled. Negative 2B, negative B plus B will be cancelled. Negative B, positive B will be cancelled. Negative B, positive B will be cancelled. We have negative B. And we've considered all things also for C. We said 1. Okay, for E also we said 2E. Mod 11 is what? 3 to the 33. If you want to calculate, let me tell you Liddell-Fermat's theorem. And in general, Euler's formula. 3 to the 10 mod 11 is 1 always. If you have a prime number, 3 to the p minus 1 is congruent to 1. It is only for prime numbers. If you want to know for composite numbers, you can send message to my WhatsApp number. Okay. So 3 to the 33 plus 33 mod 11. 33 here is 0. So we need to only focus on 3 to the 33. It will be 3 to the 10 cubed times 3 to the 3. It will be 1 times 3 cubed, which is 27, which is 5. Now, E is what? E is 6. We proved. D is what? D is 0. C is what? C is 9. And the only thing that is left to find B. 2 times 6, 12. 12 plus 9, 21. 21 minus B is congruent to 5. So, B is congruent to 21 minus 5, 16, which is 5. So, B will be 5. Okay, so in this problem, we've considered mod 10, mod 9, mod 11. We consider different mods. Let's solve next problem. It's to show that there are at least 3 prime numbers p less than 200 for which p plus 2, p plus 6, p plus 8, and p plus 12 are all prime. So it says p is also prime. P plus 2, p plus 6, p plus 8, p plus 12 are primes. Let's consider this first. Let's consider mod 2 first. So we conclude p should be odd, because if p is 2, then these numbers p plus 2 is 4. If we consider mod 3, p mod 3. If it is 0, then it will be 3, it will be 9. It's contradiction. 0 will be bad. If it is 1, then this part will be 0 mod 3, and it cannot be 3 because the previous number will be negative this one. So 1 is bad, so we conclude p mod 3 is 2 and it doesn't have problem. If we consider mod 5, p mod 5, 0 won't reach contradiction. 1, let's check 1, 2, 1, 6, 7, 1, 8, 9. 1 is okay. 2 is bad because of this. And it cannot be 5 because then it will be negative. 2 is bad. 3 is bad because of this with same proof. 4 is bad because of this. Okay, so we have. Now let's consider first these two things. From this one, it has a formula, 2 ways for finding same things here. You can find mod 6 by Chinese remainder theorem. You know that there exists. But if you want to know how to find this, it has 2 solutions. One solution, you say 2 mod 3, you add by 3 here. 2 plus 3, 5, and you will see 5 works. And then for this one, you can find p mod 30 is what? So you check that 5 mod 6 here, it's not good. If you add by 6, 5 plus 6, 11. 11 is good for this one. If you add by 6, 17, it's not good. Add by 6, 23, 29, 30. Let's check it again. 5, P mod 6 here, 5 is also good because 5 mod 5 is 0. So we have 5 and 11. Now, you can check, for example, 30 plus 11, 30 plus 5, all these things, or you can also consider mod 7. P mod 7 can be what numbers? P mod 7, we can say, and let me tell you something. If P mod 5 is 0, we can say one answer. 5, 7, 11, 13, 17. It is one of our answers. You don't need to check this part 0, which is this. So we only focus on P mod 30. P mod 30 is 11. P mod 7 is what? 0. If you have 0, it's okay. If you have 1, if you have 0, then P has to be 7 because P is prime. Then 0, 7 plus 2, 9. It is bad because 9 is not prime. If it is 1, 1 plus 6 will be 7. And then in this P won't be prime. If it is 2, then this one has to be 7. But it cannot be because P will be negative. If we have 3, then 3 is okay. What about 4? 4 is also okay. What about 5? 13? 5 for this one. Then it will be 7 and P is 5. We've calculated this here. For 5, if it is 6, for this part it will be bad. It should be 7 and P will be negative. So 3, 4. Now, if we consider, we can find P mod 210 is what? So 3, 11. So we start from this. 11, you can write 11 or 11. 11 mod 7 is 4. So 11 is one answer. 11 plus 30, 41. 41 mod 7 is 6. It's not good. Plus 30, 71 mod 7 is 1. It's not good. Plus 101 mod that is 3. Okay, so 101. These two answers are satisfied. So because it says they should be less than 200, so we should check 11 and 101. If we check 11, 11 plus 2, 13, plus 6, 17, plus 8, 19, plus this 23, it will be okay, 11. And if you check 101, 103, 107, 109, 113. Now we found all three numbers, P5, P11, P101, and we proved only we have these numbers. The next problem, it says Q. Q plus 2, plus 6, plus 8, plus 12. We have one more, plus 14. So for this one, it says there is only one. So 17 plus 2, 19. It is P or Q plus 14. It's okay. So Q5 works. If you check this one, the next one is 25, which is bad. If you check this one, the next one is 115, which is bad. Both of them are multiple of 5. So for Q, we have only 5, but for P, we have 5, 11, 101. Okay, so we worked on these ideas. And as I said before, if you want to learn all things that are useful for BMO, AMC, AME, USAMO, IMO, if you want to learn important things that are useful in Math Olympiad exam and other math exams, feel free to send message to my WhatsApp number in the description and comments. Also, we can work on the 40-50 important formulas in geometry that are useful. Also, I released a video before AMC, the day exactly before AMC, 10A and 12A 2022. And after the exam, we saw that I released another video for the solution, and we saw that there were lots of problems we could solve with the idea I released before the exam. Okay, thanks. Please don't forget to subscribe, turn on notification, and like